This lecture is about the conformations of acyclic alkanes. Conformations are defined as different 3D arrangement of atoms within a molecule due to rotations about single bonds. This part, the rotations about single bonds, is very important. Remember that there is no bond breaking occurring, so these are not isomers of each other. They are the same compound. We are just rotating about single bonds in order to find different conformations. When you rotate about a single bond, you can have an infinite number of conformations, but we will focus only on the low energy and high energy conformers. We're going to start with the simplest example, which is ethane. It consists of 2 carbons and 6 hydrogens. Remember that these carbons are sp3 hybridized and tetrahedral at the center. If we look at the 3D model, you can see that the carbon-carbon bond is in the plane of the page, and the carbon-hydrogen bond, this one here, is also in the plane of the page. And so those are represented just by straight lines. If a hydrogen is coming out of the page, then we're going to represent the bond using a wedged bond. And if the hydrogen is going at the back, that's represented using a hashed bond. There are 2 formalisms that are commonly used in order to draw conformers. The first one we're looking at is the sawhorse projection. And if we look at ethane again, now what we've done is we've put these 3 bonds in the same plane. So the carbon-carbon bond, carbon-hydrogen bond, and this carbon-hydrogen bond are all within the plane of the page. These 2 hydrogens are coming out towards us, and these 2 hydrogens are going at the back. We're going to look at this molecule from this angle. So if we look from this angle, this is going to be carbon number 1, this is going to be carbon number 2, and on carbon number 2 we have asterisked a hydrogen just so that we can keep track of it. When you convert it to a sawhorse projection, so remember we're looking down this angle, so again this is carbon number 1, it's got 3 hydrogens on it, so you can draw 3 hydrogens on it. The angles at which you draw these hydrogens are very important. So if you're looking this way, this hydrogen is going to be going directly up, and that's why this hydrogen is directly up. The hydrogen that's wedged is going to be towards your right, and that is this hydrogen. And the hydrogen that's hashed is going at the back of the page, that's going to be towards your left. Right behind this carbon is carbon 2, so this is carbon 2. And again, this asterisk hydrogen is going directly up if you're looking from this direction. And so when we draw the sawhorse projection, that hydrogen is going directly up. And then likewise we can fill in the other 2 hydrogens. The best way to visualize conformers is to use molecular models. So build a molecular model of ethane and rotate this single bond here. So you're rotating across this single bond. So rotate this single bond until you make this particular conformation. In this conformation, it's called the eclipsed conformation because these hydrogens are directly behind each other. So if I were to look at this 3D representation, this is carbon 1, and that corresponds to this carbon here. Carbon 2 is at the back, and here's carbon 2 going at the back. The asterisk hydrogen here is this one here. And likewise, you can also look at it in the ball and stick model. This is carbon 1, carbon 2. This is your asterisk hydrogen. The other conformation that we want to study is if you rotate this asterisk hydrogen by 60 degrees clockwise. So what I've done is I've taken this and I've pulled it towards myself, and now you've got this hydrogen coming out of the page, and we represented that with the wedge bond. And as you pull this out of the page, you are at the same time moving these 2 hydrogens. So as this comes out of the page, this goes all the way up, it's still at the back, and this one goes into the plane of the page. It's a little bit easier to see once we draw out both the sawhorse projection and see the 3D models. Again, I strongly recommend using molecular models to build this model, and then you can rotate around the single bond to make this model as well as the very first eclipsed conformer. So when you're translating a wedge and hash model to a sawhorse projection, Again, you're going to start with this carbon-carbon bond. So we're viewing it from this side, and this is going to be carbon 1, this is going to be carbon 2. So that means this is carbon 1 and this is carbon 2. You can see that carbon 2 has got the asterisk hydrogen coming out, which means that if you're viewing it from here, it's going to be coming to our right. And we can see that that's how we've drawn it in the sawhorse projection, where it's going to the right. In the 3D visualization, you can see this is a stick model, and so again, this is carbon 1, this is carbon 2, this is your asterisk hydrogen. In the ball and stick model, this is carbon 1, this is carbon 2, this is your asterisk hydrogen. Now let's compare those two conformers. What we've drawn is an eclipsed conformation and a staggered conformation. An eclipsed conformation is when each of these hydrogens, or whatever group they might be, are directly behind each other. That is, they're eclipsing each other. So these two are eclipsing each other. This one and this one. This one and this hydrogen here are also eclipsing each other. And this hydrogen here and this hydrogen here are eclipsing each other. If you look at the staggered conformation, you can see that none of the hydrogens are directly behind each other. So this one has nothing behind it here. This one has nothing behind it here. And this one has nothing behind it here. Since they're all out of line, it's called the staggered conformation. And again, you can look at it using a stick model, and you can see that these two are eclipsed, these two are eclipsed, and these two are eclipsed. In a staggered model, directly behind this hydrogen, there's nothing, there's just empty space. Newman projections are an alternate way to view conformers, and they're a lot easier to use than sawhorse projections in conformational analysis. So what we're going to do is use this ball and stick model of ethane and look at how to make a Newman projection. So we start with carbon number 1, and this is carbon number 2. In a Newman projection, what you're doing is you pick the carbon-carbon bond that you want to look down, and then you pull one carbon in front of the other carbon. After you swivel the molecule around, this is carbon 1 in the front, that's still in gray, and carbon 2 is in the back here, and I've highlighted that in yellow. You can see that carbon 1 still has its 3 hydrogens, and carbon 2 has got its hydrogens as well, also highlighted in yellow. Now let's figure out how to actually draw the Newman projection. Given a structure like this, first decide which bond you're looking down. For ethane, we're looking down the carbon-carbon bond, and we're viewing it from here. So just to make things easy, I'm going to label this carbon 1 and carbon 2. If you're viewing it from here, that means that carbon 1 is going to be directly in front of carbon 2. In fact, it's going to look like this picture here. So carbon 1 directly in front of carbon 2. For a Newman projection, you're going to start by drawing a circle, and that refers to carbon 1. Directly behind this is carbon 2. Attached to carbon 1 is one hydrogen that's going straight up, and in this picture, this is the same hydrogen, and we can draw that going straight up. Notice that for the carbon in the front, all the bonds are going to start from the center of the circle. Now this carbon has 2 more hydrogens. The wedge hydrogen is the one going to the right here, so we can draw that going to the right, and then we have the remaining hydrogen. And that completes carbon 1. Now we need to look at carbon 2. Carbon 2, if you're looking from this side along the C1, C2 axis, carbon 2 has a hydrogen that's going straight down. That's this yellow hydrogen here. So we can draw that starting from the rim of the circle going down. That's the hydrogen. And then we have 2 more to fill in. The wedge one, that's here going to the right, and that's your asterisk hydrogen. And then we have the one last hydrogen. And this is how you draw a staggered conformer using a Newman projection. Similarly, we can do the same thing for an eclipsed Newman projection. So remember, it's eclipsed if the hydrogens are eclipsing each other, that is, they're directly one behind the other. So these two are eclipsing, these two are eclipsing, these two are eclipsing. So now if you were to look at the 3D representation, this is an example of an eclipsing ethane. So these are the two carbons. These two hydrogens are one behind the other, as are these two and these two. Now what we're doing again for the Newman projection is we're taking this carbon, carbon number 1, and we're pulling it in the front. Okay, so we start with this carbon, we're pulling it so that it's going to be directly in front of carbon 2, and this is where it's almost directly in front of carbon 2. This is what it looks like when it's eclipsed for a Newman projection. So carbon 1 is attached to its white hydrogens. At the back we have carbon 2, and that's attached to its yellow hydrogens. When we're drawing the Newman projection, we're going to again start with the circle. Remember, the circle is representing this carbon-carbon bond. So it's representing the gray carbon in front and the yellow carbon in the back. For the gray carbon in front, it's attached to 3 hydrogens, and those hydrogen bonds are going to start from the center of the circle because that's the carbon in front. So let's also look at this structure. So if we look from this angle, we've got the hydrogen going straight up. So we can draw hydrogen going straight up. And then the wedge one is coming to the right. The hashed one is coming to the left. So this is carbon number 1. So this is carbon number 1, this is carbon number 1 here, and that's the same carbon here. Carbon number 2 has got a hydrogen that's also going straight up, and you can see what it looks like here. It's directly behind this one. Now since we have to actually draw it out and we don't want it to be overlapping, we're going to draw it a little off center. So we're just going to make it almost eclipsing. So remember that these are actually directly one in front of the other. The only reason we're drawing it like this and not like this is so that we can make out what's behind. And so likewise, we've got eclipsing hydrogens here, 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 here. So we can fill in those other hydrogens, and there's one here, and there's one here. Notice again that for carbon 2, its hydrogens are starting from the rim of the circle. If you have to plot out where this asterisk hydrogen is, it is at the back carbon going straight on top. So this is your asterisk hydrogen. This yellow hydrogen is your asterisk hydrogen. So now let's compare the Newman projections of the eclipse and the staggered. And you can see that it's immediately easier to see what's eclipsed and what's staggered when you compare it to a sawhorse projection or even a wedge and hash projection. So this is carbon number 1. This is carbon number 1 in the front. Again, carbon 1 here, carbon 1 in the front. You can monitor the rotation. So we started with the asterisk hydrogen directly eclipsing this one. So this asterisk hydrogen is directly eclipsing this hydrogen here. We've rotated to move the asterisk hydrogen out of the way from the first hydrogen. And so you can see that now we've rotated it to move it till here. Okay, so we've moved this 60 degrees to the right, and we've got it here in its staggered conformation. So you can see that eclipsed and staggered conformations are just 60 degrees apart, and you can keep going. So you started here where it was directly behind this hydrogen, we moved it 60 degrees, and we ended up with this staggered. We can move it another 60 degrees, we'll end up with another eclipsed, and then we can keep going all the way 360 degrees around. It always helps to build molecular models or see some type of 3D representation of these molecules. This is the eclipsed version, this is the staggered version. I encourage you to take molecular models and build eclipsed and staggered and keep rotating it and see the different conformations.